Thank you, everyone. So, I hope my screen is visible and am I audible to everybody?
Yes, sir. Visible and audible, sir.
Yes.
Yeah. So we can directly start. I see many of my already known people have joined the webinar. So welcome every one of you. So presently I am at Nainital Aries. So if there is some hindrance with a network or something, I have already shared my PPT with Shubhankar sir. So at that time he can share the PPT because there is possibility there. This is a remote place, so electricity sometimes might get off or there the Wi-Fi can go slow down. So, apart from that, let us start with this interesting topic of spectroscopy. As many of us already have some idea, many of the group members who have joined, they are doing some projects on citizen science, contributing in astronomy with their capacity. So, spectroscopy is definitely the science, or spectroscopy is definitely the technique by which we can study the universe, basically the universe, especially the stars or any object which is very far away from us in the universe. We cannot touch them, we cannot bring them to our lab. So but basically we need a communicative language to study them, right? And that language for astronomers is spectroscopy. It is the tool through which we have understood what is present in the universe, their properties, mostly. So if we go to India, see, this is the definition of astronomical spectroscopy. It is a boring definition. It's difficult to understand what it means by reading these 3 4 lines. So it is a study of astronomy using the technique of spectroscopy to measure the spectrum of electromagnetic radiation or light, including all types of light which is radiated from stars or other celestial objects. But this boring term becomes very fascinating if we try to look at this picture. This also defines what is spectroscopy. This is the picture of what we all know by our common sense and understanding nowadays, that these are stars. But apart from that, can we say something more just by looking at this image? We cannot, because this is just an image without any information. We can tell that, okay, there are stars which are of different colors, and that's all. But if I now say this is an image of more than 250,000 stars very near to the center of our galaxy, around 26,000 light years away, in a region near to the Sagittarius constellation, and this picture has been taken by obviously Hubble Space Telescope. And this information which I am sharing, how do we know that? This is mostly by using techniques, astronomical techniques. And a major technique is spectroscopy, which we definitely tell as the language for communicating with stars. So stars basically also have a language which is not a basic literary language. They also talk to us with their own scientific language. And that tool or that language is spectroscopy. By the help of this technique, we can actually understand, we can actually predict the evolution of each and every star which we see in this picture. We also know about the properties of these stars if we can study any of these stars using spectroscopy. We know much more than ourselves own than that what we know about stars. Basically, what I want to say is our knowledge about stars is much more than what we know about humanity as a whole. And this knowledge, how we can predict, how we know about stars, how we can communicate with stars through this particular spectroscopy technique, is a fascinating journey. If we go bit early times, there are so many good books, good articles which tells the history of spectroscopy. At the last, I will also refer some of them. But very basically, spectroscopy began with Isaac Newton. We know that in the earlier 17th century, he was the person who split sunlight into a spectrum of colors. What he used? He used a simple prism. So sunlight used to come through a small hole in his room or in his working place. And through that hole, when is coming, he just put the prism in front of that sunlight. So he found that that sunlight, which is basically what we think is whitish or yellowish, sometimes it looks like yellowish in color or whitish in color, that sunlight broke up into 7 distinct colors. So this was the first time that radiation or sunlight broke into its component colors, and the spectrum, or these colors which he was able to show in a screen, and that produced the solar spectrum or the sunlight into different component colors. Now the problem is that, what does it mean? So with a simple prism, if you split the sunlight or any light into its component colors, you might not be able to understand. You will only see the spectrum, so many colors, and that's all. But it took around more than 50, 70 years, around 100 years, to understand that splitting of the color is not only just a funny thing. It can tell us so many things about the object from which that light is coming or radiation is coming. So it was in 1802 when this English chemist William Wollaston, he also did the same thing. He also split, with the help of a prism, the sunlight was split into a spectrum, and he noticed so many dark lines like this in the solar spectrum. He was the first person to notice these lines. Within another 10, 12 years, this person we know everybody, Joseph von Fraunhofer, a German optician. He was not a scientist, he was an optician. He took the charge and he actually catalogued over 570 these dark features in the solar spectrum, and these particular dark lines he marked with the numbers or letters. So when we say that we are watching Fraunhofer lines, that doesn't mean that something else. These are the lines which he catalogued and he marked like this. Now, the issue is, during those days, during those 1814, they were not able to properly understand how these lines are formed. But it was Fraunhofer, though he was not a scientist, he can literally be called as a genius. He was able to predict that these lines are produced by elements which are present in that particular object. That means sun. So by the process of this intuition and very simple experiment, he was able to identify the element sodium in the solar spectrum. This was the first element which was identified in a spectrum of any astronomical object. What he did, he actually found that there is a yellowish color. Near to that yellowish color, there is a line in a particular wavelength, and that is also looking like bit yellowish. That was an emission line, not dark line. So that yellowish kind of line he was able to identify as sodium. How? What he first guessed that might be sodium, and he sprinkled in front of a candle, he sprinkled salt also has sodium. And when he took the spectrum of that salt, he also found the similar emission line, yellowish line, in the same wavelength region. So he was able to predict that this line corresponds to the sodium line, or that particular yellowish line which he is watching in the solar spectrum. So this was the first time he was able to identify that sodium is present in sun. Now after that, people were not aware how these lines are produced and what we can understand from this. So during 1850s, these are two very famous names, Gustav Kirchhoff and Robert Bunsen. Many of us, mostly all of us, must have heard about this term, Kirchhoff's laws or Bunsen Burner. So these two are the people. They were not physicists, they were basically chemists. These Fraunhofer lines basically are what? They are basically emission lines which are identified in the spectra of heated elements. So as I have told already, that if you heat any element and take the spectra of that element, then you will see lines, you will see emission lines, you will see very bright lines, and that bright lines will correspond to particular wavelengths. Likewise, these people were also able to identify that means in the solar spectrum, the dark lines which we are noticing in the solar spectrum, in the previous slide, you see these dark lines, what we are noticing, they should originate not from emission but from absorption by different chemical elements present in the atmosphere of sun. Now, what does this mean? So this identifying or this characterization that how these lines are formed or why these lines are formed became the major work of both of them. And Kirchhoff was much more into it. He went more into the deep part of this, how the lines are formed, and ultimately, now we know the famous Kirchhoff's laws of radiation, that how a spectrum is created. So basically, spectrum is created by these three processes. Or we say very easily that there are basically three types of spectrum which we can see for any element. Let us suppose, for the first case, let us suppose there is light, or there is a source from where hot radiation is emitting or hot radiation is generated. See, if the hot radiation is generated, and if we put, just like in Newton, if we put a prism inside that or in the path of that hot radiation and then take the spectrum will be like this, with no lines in it, no dark or bright lines in it. This will be a continuous spectrum. This is known as a continuous spectrum. But basically, getting a continuous spectrum is in theory only. We can get it in theory. Practically, if generally we don't get a continuous spectrum. Why? Suppose there is a hot gas. There is a hot diffuse gas, low density gas, and that gas, the radiation coming out from that gas is passing through a prism. And then we take the spectrum of that. Then we will see the spectrum is like continuous spectrum, but there are some bright lines superimposed on that continuum. Now, what these bright lines are telling, these bright lines will appear at very certain wavelengths. And that gives like a fingerprint of those elements which are present inside this hot gas. So that means if we can study the spectrum of any particular gas, and if we study at which particular wavelength there are certain lines which are produced, emission lines, we can tell that those particular elements at that particular level or that particular intensity is present in that hot gas. So this type of spectrum is known as an emission line spectrum, means hot diffuse gas, low density gas producing a emission line spectrum. But certainly in case of stars, mostly in case of stars, we see the opposite case. We see a spectrum where there is continuous spectrum and there are dark lines. What does this mean? This means that if, suppose you take this particular same picture, if radiation is originated from a hot source, in case of a star, the hot source from where radiation is generated is the core of the star. Very hot. From this core, the radiation is generated, and then it passes through cooler outer layers of the star. That is the photosphere, the other layers inside, radiative zone, convective zone, photosphere. And after that, so these layers are behaving like cooler outer atmosphere of the star. That means cooler gas. And inside there is the core, which is hot. So radiation emitting or originating from hot gas or hot source, and then passing through cooler gas in case of star, that is the outer layers or outer atmospheric layers. And after that, we take the spectrum. Then we will see a spectrum having dark absorption lines. And these absorption lines tell us, similarly, the elements which are present in that outer layers, not inside the core. Because the spectrum or the radiation whose spectra we are taking, that is originated from the outer layers, especially the photosphere, the surface of a star. So in sun, we call that surface of a sun is we call the surface which we see in case of our daily day-to-day life. That is known as the photosphere of the sun or photosphere of a star. So when we see the spectrum of a star, this spectrum tells us what are the elements which are present in that photosphere, nearby to that photosphere region. But if we want to probe deeper, there are other techniques. So because we cannot see what is inside the star, there is almost no way to see that, no direct way. So the question is, okay, through intense studies of the known elements, we know that elements, when they are heated at what particular wavelength, they will produce lines, either absorption or emission. So now if we compare that with that of a solar or stellar spectrum, we can identify that this particular line at a particular wavelength is produced because this particular element is present in the photosphere of this particular star. This is like a fingerprint. One can ask why emission line and why absorption line. I will come to that. What is why physically why these lines are produced. So until in 1850s, 1870s, 1900, before the era of relativity, before the era of quantum mechanics and quantum physics, before we had an understanding of atomic physics, what is an atom, how an atom looks like. So before these came, we had a good understanding, basic understanding, how spectrum is produced and what kind of spectrum can a star or a body give. So basically, we can have three types of spectrum. In real bodies, we will actually see either emission line spectrum or absorption line spectrum. And how these three spectrum are formed consists of the three famous laws of radiation of Gustav Kirchhoff. So this was the understanding before the starting of atomic physics, before 1900. So this, what I have already told, is shown in a picturesque scale. So same thing, there is a hot bulb, or suppose you can take this is a star. If there is a hot bulb or any hot body, it is directly coming to the, or if suppose this is sunlight, directly we are putting what is slit, I will tell later. So if we are taking the spectrum of this directly, then it will look like a continuous spectrum, but this doesn't happen because stars are very far away from us. Even sun is 15 crore kilometers away from us. So if we take sun, or if we take solar spectra, then what we actually see is not the spectra or not the radiation coming from the core of the sun. Naturally, solar spectra looks like this: absorption spectrum. That means what? The second case. So radiation is produced at the core of the sun. After that, the outer layers of sun are cooler. And if this is the photosphere, the last layer, this is the photosphere from where the radiation is coming and producing the spectrum. So we will see dark lines, and these dark lines, if we can compare, then it will tell us which are the elements present in the photosphere of sun. And the similar case can happen in case of emission line spectrum or emission spectrum, where this gas, if it is dense, if it is not so dense, so if this is instead of cool, if it is a hot gas, then it will produce emission spectrum. So this is how a spectrum is produced. Three types of spectrum. But basically, from the age of quantum days, 1900 onwards, 1915, 20 onwards, when we had a good idea about atomic model. What is an atom? What is an atom made up of? What is matter made up of? We had to wait till then to understand why emission lines and spectrum, or why these emission lines and absorption lines are seen, why at particular wavelengths it is seen, what physical process is happening so that these emission lines and absorption lines are produced. So let me give a very basic idea how spectra is produced. First of all, we know that what is an atom. Basically, atom, what an atom consists. Atom is, we know, is one, it can be one of the small parts or smallest part of a molecule or of any matter. Now what an atom consists of, it consists of three things mainly: neutron, proton at the nucleus region, and electrons orbiting an atom. So the simplest atom is definitely of hydrogen, where we have one proton, there is no neutron, one heavy proton, and there is only one electron revolving around this proton. This makes one proton and one electron makes an hydrogen atom. Now suppose when I am telling that electron is revolving around hydrogen proton, at what distance from the proton the hydrogen electron is revolving, that distance is important. So there is definitely an average distance where the electron generally remains, and usually remains if it is not heated, if it is not excited, if it is not affected by any other physical force or something else. So this non-excited, non-disturbed position, non-disturbed atom of a hydrogen or any other element is known as the electron is in ground state. That means in general case, if we are Superman, if we can see the atom of a hydrogen, we will see, basically not, but basically let us take that we can see very easily like this. So we can expect to see that there is a proton, and at a certain distance there is an electron revolving around that proton, making a hydrogen atom. Now, this basic ground state, or at general state, this distance at which the electron revolves, this is an orbit. Now, this orbit can change. We call this ground state orbit as equal to the first orbit of the electron. Can the orbit of that electron change? Can that electron of the hydrogen atom go away from it? Means jump to higher orbits, jump to higher energy levels? Yes, it can. So as you see, suppose due to some reason, the electron from first orbit, it jumps to a higher level or a higher position, then we say that in that case it is in excited state. The atom of hydrogen is in excited state. So this is how this jumping of electrons, in scientific term what we call as transition, this transition of electrons in every element due to excitation forms the basis why spectra forms, why emission lines and absorption lines form. Basically what happens, if suppose now if I come to that solar spectrum, try to think about that solar spectrum. If I try to give the physical explanation of that, why we are watching absorption lines. See, the radiation which is generated from the core, that is very, very hot, extremely hot radiation, extremely, if I call it very easily, light, extremely hot light or radiation. That radiation, when it is passing through the outer layers, suppose this is the outer layers of sun. When it is passing through the outer layers, we know at photosphere of sun what is the temperature, around 6000 degree, 5800 degree Kelvin, which is very less compared to the core. So suppose at that temperature, when radiation is passing, that hot radiation is made up of highly energetic photon particles or photons. And in that hot atmosphere, in that so-called cooler atmosphere of the photosphere, it is made up of hydrogen, we know. So what will happen to the hydrogen atoms? Hydrogen atoms, the electron of hydrogen atoms, they can absorb energetic photons from that hot radiation. And if suppose they are gaining some energy by absorbing photons, then what will happen? Some of the electrons of the hydrogen atoms, in different hydrogen atoms, they will come from ground state. Their electrons will jump from lower energy level to higher energy level by gaining photons. Now you see, when we take the spectra of that particular radiation coming out of that photosphere, what we will see? We will see the spectrum of light where some of the photons are missing, because some of the photons have already been absorbed or captured by the electrons of hydrogen. And as a result, we will see those absorption lines like this. These are the absorption lines. And especially, very, very specifically, this particular line, you see, this particular line. This particular line is what, just giving an example, this particular line is telling it is produced at a wavelength of 6563 angstrom. At that particular, so this absorption of photons can happen at very particular energies. Electrons of hydrogen cannot absorb as much as number of photons, or photons of so many energies, they cannot do that. Photons of particular energy can be absorbed by hydrogen atoms or electrons, so that the electron will move, suppose from orbit number 2 to orbit number 3, means more higher orbit, orbit number 2 to orbit number 3. And if this transition happens, then the photons which are absorbed, they are missing. And as a result, an absorption line will be produced at 6563 angstrom. So by watching this line, this is known as, technically this is known as H alpha line. And by watching this line, what we can say, that hydrogen is present in the atmosphere of, or in the photosphere of sun. Now hydrogen of what level, what energy, that also we can tell, because at what kind of energy is absorbed to produce such line, we can now understand. So this is what a Bohr atom is. This is what I have explained till now. Is suppose you see that this is an atom of any particular element. There are protons inside. Now electrons are there. So for suppose if we take carbon, in the first orbit of carbon there are 2 electrons, second orbit there will be 4 electrons. Suppose for hydrogen, if we take, for this is the simplest atom. For hydrogen, if we take, then what will happen? Suppose from the first orbit, as we have seen the previous case, from the first orbit the jump is happening to the second orbit. So first to second. For that, how much energy is required? This is what is written here. 10.2 electron volt of energy is required. If photons having this much energy are traveling nearby, then there is a possibility that electrons can absorb those photons of this much energy, and those photons will be missing. And as a result, we will see a particular line in the spectrum. So this is how a spectrum is produced, very basically. So the jumping and the transition of electrons from lower orbits to higher or higher orbits to lower. Now we can understand, we can basically get a basic idea what is absorption line and what is emission line. Absorption lines will be produced if an electron jumps from lower orbit to higher orbit, because they are absorbing some photons, they are absorbing energy, gaining energy. As a result, it is jumping to the higher level. If opposite happens in case of an emission line spectrum, that already the hydrogen, the electrons of an element are already situated in the higher orbits and they are jumping down by emitting electrons, photons. So that means there will be extra photons, and that extra photon energy we will see in the format of emission lines. So we have names for these lines. Any transition happening from the first orbit to second orbit or first orbit to third orbit means that if the transition starts from first orbit towards some higher orbit, we call those lines for hydrogen Lyman series of lines, because Lyman was the scientist who first identified this series. Second, suppose in case of another set of transition, we see that from the second orbit, so electron was already in the second orbit, second level of energy means the electron already had this amount of energy and it was already in first excited state. Now from the second orbit, it has started jumping to third or fourth or fifth higher orbits. So that series of lines are known as Balmer series. If the same thing happens from third orbit to higher level, then these are known as Paschen series, like this. So this is a very basic idea how spectra or how absorption and emission lines are produced. But my friends, we have to understand the thing what I have explained is not so easy. It is not so easy because in stars, in other areas, in astronomical objects, we are only not dealing with atoms. We are dealing with molecules. Molecules are made of so many types of atoms. So they can become, the spectra can become more complicated and more tricky. Also, if really we are a superman or a human, if we can go and look at how an orbit or how an atom looks like, do you think that you will see hydrogen atoms so clearly and cleanly that there is a proton and there in a particular orbit there is an electron rotating? Or suppose carbon atom, there is some protons, neutrons, and 2 electrons revolving in a particular orbit, 4 electrons revolving another orbit. So neat and clean picture? No, we will not see that because of quantum physics, uncertainty principle. So we will see like this. So basically, we can never become sure at what particular position an electron will remain. We can either predict how fast it is rotating, what is the spinning rate, or we can predict at what average position the electron will stay. So as a result, if we are really superman, if we can see the atom of any element, we will see something like this. It's like a cloudy, patchy pattern, not so clean like this. So as a result, what we are actually telling here, that from one particular orbit the electron can jump to second orbit. Why cannot can the electron jump from here to here in this region? It can, but for a very, very, very small amount of time without going to any other physics details. Now these things make atoms and spectra very complicated and also very interesting. So there are so many positions, so many states, so many levels where an electron can jump. This I am explaining with the simplest atom, that is hydrogen. Now you consider higher atoms or higher electrons or higher level of atoms where there are so many electrons, so many protons, so many things that there can be numerous amount of such jumps, such infinitesimal number of lines can come or lines can form because of so many transitions which are happening, numerous transitions. And this is where the importance of spectroscopy, to understand spectroscopy, came. So basically now, during if I consider 100 years ago, during the time of 1920 or 1919, this was, we understood how an atomic spectra, how a spectra forms. But the problem is that, see here, it is very clearly written. Suppose this is the Lyman series of hydrogen lines. Means Lyman series means the electron will jump from either level number 1 to 2 or 1 to 3 or 1 to 4, and at what wavelength they will produce a line. This is written here. Nanometer into 10 means that will be angstrom. So now if for hydrogen, now let's take a particular star only having hydrogen, nothing else, no molecule also, nothing else in its atmosphere. Can you get an idea how many different lines can be produced? So many, right? Because Lyman series, you see, if an electron jumps from 1 to 2, then there is a particular line and a particular wavelength. 1 to 3, again another line. 1 to 4, again another line. What if 2 to 3, that is the Bama series? 2 to 4, 2 to 5. What if 3 to 3, 4? What if 4 to 5? So a single element, the simplest element having only one electron, can ultimately give rise to numerous emission or absorption lines, spectral lines. Think about complex atoms, they can give numerous number of lines. And this was the greatest discovery by an Indian physicist known as Meghnad Saha. So during 1920s, people became almost confused that, okay, because how many elements, how many different types of elements we know till now? Around 92 are naturally occurring elements, and another 18 to 20 what we can prepare. So around 110 or 105 or 110 elements are there in the universe, with which everything is made up of. So if every element has a particular signature, particular fingerprint in spectra, if an element can produce a single line, particular single line, then we can expect 110 different lines in 110 different wavelengths. But if we take solar spectrum, we see millions of lines at millions of different wavelengths. You see different lines. So people were definitely confused during those period. That means, is our physics wrong? Is our understanding about nature completely wrong? Are there millions of new elements which are not till now discovered? The person who solved this with a blink of an eye, with one single equation, with one simple, having no funding, having no security of job, having almost no benefit, that person was Meghnad Saha, working at Calcutta. And that famous equation is known as theory of ionization potential. He was the person who first developed that equation and was able to prove that, see, my friends, our physics and our understanding about nature is not wrong. See, a single element, the simplest element is hydrogen, can produce numerous lines, not one particular line. Because why these lines are forming? Because of transitions and transition possibility, whether that particular line can transition, can happen in a particular star or not, that is also that can also be calculated with that equation. So this radically solved, within a day it solved the problem that, okay, we need not have to scratch our head. We need not have to think that there are millions of elements which we have to discover. What we know is correct, and we have to progress with this already understood knowledge. So this is why the theory of ionization potential equation is extremely important. This discovery is regarded as one of the groundbreaking, path-breaking discovery in the field of spectroscopy, and he is known as definitely the father of stellar spectroscopy. And stellar spectroscopy from that day onwards progressed satisfactorily. So if we see the, the spectra of a element, what I have told till now is by numbers, by physics. Now let us see how the spectra of an element looks like. See, this is hydrogen. So basically, if we take, as I have told, that any atom or isotope or molecule, they have a particular fingerprint, and they will produce lines, either emission line or absorption line, at particular wavelengths. So see, hydrogen line can produce emission lines at particular wavelengths. Why this line is happening? Because the transition is occurring for an electron in the hydrogen atom from a particular level to another particular level. This line is happening. Why it is coming? Because the transition is happening from a different level to a different level. That's all. So is about sodium. So this yellow line was first discovered in the solar spectrum by Fraunhofer. Helium. Now as we go towards, you see, more complex and more heavy atoms, you see more and more different types of lines which they can form because they have more electrons. So this is how the elemental spectra looks like. If we take the spectrum of a hydrogen element, and if you go on taking the spectrum in different ranges, it will show lines like this. These are all emission lines. And in basically, before the invention of computers, before the invention of digital technology, spectra of a star or an object was taken like this. So the spectra was taken in a photographic plate, where among the black background, on the silhouette of the black background, we will see emission lines as bright lines, and the dark absorption lines will be much more darker than this background. But now we have digitization. We can record the spectra. We can convert these light signals into electrical signals and record the spectra in digital format. So if we take different types of stars, spectral type of stars, O type, B type, F type to M type, different types of stars if we take, we will see different lines coming. See, this is the continuous spectrum, and all stars are showing absorption lines. See how many absorption lines, all black lines are actually spectral lines, all. So there are millions of lines here. Definitely the most prominent are these lines, which are some case hydrogen, some case helium, according to the spectral type. So this is how the spectra looked like if you take the spectra of a star in a photographic plate. But it is difficult. It is very difficult to measure the parameters, to measure the intensity, to measure the properties of that line from a photographic plate. And this is why technology is important. Nowadays, we have, as I have told, digital technology, digitization. So now the spectra of a star looks like this. So it's like, you see, it's a mathematical, it's a software, it's a tool. It's a mathematically we can record that spectra. Digitally we can record the spectra in the form of electrical signals. Here you see in the digital format, we normalize the spectra which we are obtaining, the signal which we are getting, that signal or noise, we normalize it. And after normalization, we find something which is a continuum. As I was telling, continuum spectra, this is the continuum. And any line which is jumping above that continuum is an emission line. So this is that particular H alpha line or hydrogen alpha line from Balmer series. These are, some of them are Paschen lines, some of them are calcium lines. Now we can, if we zoom in the software, so this is the importance of software. We can zoom it, we can see the expanded view, and we can look into, we can measure the spectra, see the lines here. When we have zoomed that region of Paschen lines, see these are Paschen lines, these three are calcium lines, this is oxygen 1 plus Paschen. So these are the lines, and see, this is the continuum. So any line which is substantially above the continuum is an emission line, and anything which is below the continuum is an absorption line. This digitization has made it very easy for us to study the spectrum, to study the parameters and properties very easily. And when we represent it, this is how the basically, if we take the spectra of a star right in the whole, the visible spectrum of a star. So I study a particular type of stars. For our stars, this is the spectra, how it looks like in the visible spectrum. In case of astronomy, mind it, in astronomy, we call 3,800 angstrom to 10,000 angstrom as visible spectrum. And so 4,000 to 7,000 is what our eyes can detect, but astronomical CCDs can detect 3,800 to around 10,000 angstrom. So in that, almost in that range, these are the lines which we see for our stars. So you see H alpha, you see iron lines, you see calcium lines, Paschen lines, O oxygen lines, like this. So basically, now let me give a very brief idea how we take the spectrum, how we convert the light coming from the star to a spectra. This is how the spectroscope of a basically astronomical telescope looks like, very basic. So what happens that so it's an instrument which is placed with the telescope, on the telescope. It is mounted on the telescope. So what it does, from light from the star comes, and from here the spectroscope starts. Inside the spectroscope, these all components are there. So there will be a small slit, means a small opening, through which a particular amount of light can only enter out of, not, we don't want all the light coming from the star, because there will be so much of background light coming from other stars, background, and all these things. So what we will do, at the focal plane of the telescope, we will place a slit, small opening through which a particular amount of light will come, fall in the mirror, inside the spectroscope. After reflection, we will put a grating. Now, this grating will ultimately do the work of that prism. It will break the light into its component colors. And through that component colors, again, passing through the mirrors and other places, we will ultimately put the CCD or photo detector here. This photodetector will very specifically convert the light into electrical signal and spectra. That electrical signal is converted to spectral lines. So see, here we see an absorption line. Now, absorption line of which element we can study using your knowledge and your experience and the basics with the help of software and all these things. So then the analysis starts. But mind it, the spectra through which the spectra which we will receive in this process, what we call it as raw spectra, means, see, it is very important in any study, in any research, to understand the importance of data which we are studying. The data which we are getting here is in the form of lines or spectra. So this spectra is this, that means what? It is coming from the radiation which is coming from the star. Whatever we do, see, it is an instrument. There are so many instrumental limitations. So as a result, whatever we do, however small the slit is, some background light will come. Also, there can be other effects like cosmic ray can come. So the spectra, by this process, what we are getting from a star, the whole radiation which is converted into this signal, that whole radiation might not come from that particular star. Some photons or some noise, that is what that unwanted photon or unwanted signal, what is already embedded, what it comes here with that starlight, is known as the noise. So that noise or that unwanted photons can come from background, come from cosmic rays, come due to instrumental limitations, instrumental built up noise, all these things. So the data which we receive by this process is a raw data. That raw data we have to ultimately convert to a usable data, and this process is known as data reduction. So the raw data which we will receive, we cannot study the star, we cannot study an astronomical object with that raw data, because there will be so much of unwanted noise in it. That unwanted noise we have to reduce, we have to delete as much as possible. That we do using a process known as data reduction. So for stars, for objects, we have that standard process in our universities. We train our especially MSc students to do this, who are taking astrophysics as their specialization. They are trained for this data reduction, and that also gives them a proper flavor of contributing in astronomy research. So some of them have done good work, data reduction of more than 500 stars somebody have done. So we have also given them the credit of co-authorship of a paper, because without this proper data reduction, we will not get a proper data will not come. And that proper data will only scientists can or researchers can analyze. So this is how the process goes on. This is how we get a spectra of a star, basically. There are so many other things involved which we are not telling. Now, what it tells us, what the spectra, now we understand how a spectra is formed, how we get a spectra basically. And by reading the spectra, by reading the language of these stars, what we can tell about them, we can tell almost about most of the major properties and evolution of the stars can be told by spectroscopic studies. So this spectral classification of stars, which I believe that it is many of you are familiar with this classification, that stars can be classified into 7 major types: O, B, A, F, G, K, M. And why such odd names? The spectral classification of stars started in Harvard University in 1880s. This is a fascinating story. You can read about it, how stars were classified. And mostly, basically, women should feel proud that during that time, it was women were not allowed to enter Harvard University. So the then director of Harvard University, means Harvard College Observatory, Edward Pickering, was very adamant. He told he was also fascinated by women. So he was very strong that I will only take women assistants to classify stars. Spectral classification of star was a major project at that time. So this spectral classification was done under the leadership of Edward Pickering. Around 10 wonderful, very talented young women that joined those group. They were known as computers. And very luckily, I am proud to say that almost all of those 10 women became world famous astronomers in future. Means not only world famous, they are legends. One of them was Annie Jump Cannon, one of them was Henrietta Swan Leavitt. These were some William Enough Stephen Fleming. They were very big astronomers. So Annie Jump Cannon was the first person who classified manually more than 2 lakh stars, spectral classification, and she made a classification scheme by watching the strength of hydrogen lines. And she told that, okay, stars can be classified into A, B, A, E, like that, simple, A, B, C, D, E, F, G, H, like that. Gradually, better understanding when it was understood, then the spectral classification of stars started following the temperature sequence. The hottest stars are actually O type, so this O type is placed first. So like that, the hottest star is O, then B, then A, going to M. So maximum of the stars in the universe will fall in this category, in this one of these 7 categories. And now you see the temperature of these stars, the color, and definitely the temperature of a star will determine its color, its outer color, photospheric color. So when we see these stars, these all stars are observed in the sky during different times with naked eyes. That's why I have put these stars. So you see the colors of these stars, just by looking at the color of the star, you can now tell some of the things. Its outer temperature, its spectral type, basic spectral type, how it will evolve, what is its age, basic things you can tell. Not very properly, but basic. So now if you remember the first picture which I have showed, just by looking at the color of those stars, we can actually say so many things about those stars. And for very precise understanding, we need detailed spectroscopic studies, other studies also. So see, this is the spectral type of stars, the spectral classification. And for O types, B types, these are the main spectral features which we see in the spectra of these stars. This is noted down here. And if we move, what else we can see? What else we can do with the help of astronomy, with the help of spectroscopy? This is a very familiar image or very familiar thing or very familiar property dissemination which we can do is understanding the motion of objects in space. including stars. So what we see, if any particular star is coming towards us, then we will see particular lines in that spectra shifting, shifting towards bluer side, and which is known as blue shift. This Doppler shift will happen. And if we see, or if there is a star or any object in astronomical or in the universe which is moving away from us, then we will see the lines, those particular lines which should be formed at particular wavelengths, they will not form at that particular wavelength. They will be moving towards redder end. But if we see a non-moving object having no motion, then the lines, as I have told, that then the lines will be formed at very, very particular wavelengths. Suppose if this is H alpha line, it will form at 6563 angstrom. In case of any particular star, taking care of all other parameters, if we see that a galaxy or star, that's instead of forming here, the H alpha line is here, shifted towards blue. That means the star or the object is moving towards us. It is showing blue shift. And opposite, if it is moving towards red. So the motion of astronomical objects can definitely be studied with the help of spectroscopy, but this motion, to study that, the object should be very far away. The nearby stars will show you so less motion that it will be almost unidentifiable in spectra. Then let me give, I don't want to go to mathematics and all these things, just to give an example how precisely we can tell about the properties of a star with the help of spectroscopy. See, we know if you want to study, if we actually study how a black body curve looks like and how the black body of an object helps us in determining the position or the temperature or size or other aspects of a star. So considering sun as a black body, definitely sun is 10 minutes more. Yeah, I am almost over. Yeah. So yeah, what I was telling is, see, in normal cases, stars, as I have told, it will definitely show you absorption spectrum, because following Kirchhoff's law, because the outer layers of sun or the star will be less hotter than the radiation coming out from the inner core. So we expect absorption lines. But there are some peculiar stars, strange stars, which show emission lines in their spectra. That doesn't again mean that our physics is wrong. And I do work on this peculiar or rare kind of stars, which are known as emission line stars as a whole. There are so many types of emission line stars. So classical BE or AE, these are types of emission line stars. So specifically, my work is on a particular type of emission line star, which are known as classical BE stars. What does that mean? That is how suddenly a star can give you an emission line. This is how it can give. Suppose there is a star, very hot star, and that star is surrounded by a disk, equatorial disk like this. Then when the radiation is passing from photosphere, it will then pass through this huge disk, gaseous disk. And this disk is the place where emission lines are formed by a process known as recombination. So I'm not going to all this physics. So as a result, if we now study these emission lines coming from these stars, we can actually understand the properties of this stellar disk and how this stellar disk behaves. What is the connection between the star and the disk? So to understand disks, astrophysical disks also, in case of astronomy, we take the help of spectroscopy. Definitely we take the help of spectroscopy. I am doing spectroscopy to understand the disks of a particular type of star. Somebody else is doing for other things like protoplanetary disks, accretion disks around black holes and other energetic objects. So you see, it's not about only stars. I'm just trying to say that spectroscopy has become a tool to see the universe, to study the universe. It broadly can become the language of the universe, not only of the stars. So this is how spectroscopy is helping in various aspects. So these are some of the telescopes, very prominent telescopes having very, very powerful spectroscopes of India, astronomical spectroscopes. So we use the data coming from these telescopes. And if you see this 40-inch or 1-meter telescope at Kavalur, you see this is the telescope. Many of you are familiar with this telescope. At the end of this telescope, you see something here. This is the spectroscope. This is the spectroscope inside which the all the components, as I have shown, there are so many components doing so much type of work, critical work, and we are ultimately getting the spectra. So this is how it works basically. And well, I would like to stop. And before stopping, before opening for questions and discussion, see if anyone would like to read an article, a popular article about spectroscopy and how spectroscopy has been developed in case of stellar spectroscopy. This is an article which you can read. And one paper, this is a paper about what is an astronomical spectroscope and how an astronomical spectroscope works. This is a wonderful paper. So these two I would like to refer. You can go and have a look into these objects. And if so, in this citizen science group, I can share a book because in the WhatsApp that is a book on astronomical spectroscopy. Basically, that gives us an idea how the spectra of every kind of star looks like. So that book I can share in the group definitely. No need to, or one can download also. It's very costly. No need to buy it. So thanks to everybody, and we can now, if anyone has having any question, any comment, we can have that. Thanks to everyone.
Thank you, sir. Can I
Thank you.
ask?
Thank you, ma'am. Yeah, ma'am.
Uh,
Sure.
yes, it was very nice presentation. We are very much enriched with your talks and illustration. Sir, I have two questions. You just mentioned the Shaha ionization equation. Can you please tell us how this equation solves the spectrum related?
Yes. See, the thing is that what Shaha did actually. See, Meghnad Shah was the person who was able to identify that. See, we see so many. Take solar spectrum. We see so many lines. That doesn't, is what Shah told, that doesn't mean that so many types of new elements are there. What it means is that at a particular temperature, what is present at solar atmosphere or photosphere, at that particular temperature, which elements can produce lines at what wavelengths, means which transitions of which element is possible. That was the problem which was solved by this equation. So when we say, if you take a star spectra and if you see very faint hydrogen lines, or if you don't see, suppose, helium lines, does that mean that helium is not present in that star? No. At the from the temperature from where the spectra is originating, the temperature might not be proper or might not be suitable for helium transition to occur at those levels. As a result, we are not watching helium or hydrogen, more intense hydrogen. So if we take, suppose if I give an example, hot stars, suppose O type stars, you will see hydrogen, but very less intense hydrogen. Does that mean that hot stars are not made up of hydrogen or less intense, less amount of hydrogen? No. But instead, you will see in hydrogen becomes very intense in the spectra of A type stars. Does that mean that more amount of hydrogen is present in A type stars? That is not the case. So this was the major problem in those days. People were confused that is hydrogen having different property, or the stars are made up of so many different new elements which we don't know. That is not the case. So Shah was the person who told using that equation that basically we are not watching most amount of hydrogen in case of O type stars because at that very hot temperature, ionization or those transition of hydrogen is not possible up to a certain level. As a result, we are not watching that amount of hydrogen. So this ionization potential theory gives us this. We can calculate what kind of transition will be possible in what temperature, and as a result, what kind of spectra we can expect in stars. Yeah, so this is the problem which was, is a very typical problem which was solved by Shah. Yeah, so I
That
feel
means it depends on the temperature of the
it's
stars.
temperature dependent.
At,
Yes,
yes,
yes, it is
yes.
dependent on the temperature.
And my second question is that you said that we generally get the absorption lines from the stars.
Hmm.
but does not we get the emission lines? Only for you mentioned that for B star we only get
No,
the
we get lines.
emission lines.
Yes, yes. We get emission lines only if there is something or some gas disk or some disk-like structure or gas or dust surrounding that star. Otherwise, we will not get. And this is the thing. Otherwise, the from photosphere, we will not get emission line. From photosphere, we will always get absorption line because of Kirchhoff's
But
second law.
why for B stars there are a disk
Because
of
for these,
some
yeah, yeah.
luminous object.
No, not
That's
luminous
why we
object.
get.
It is a cool, it is a cooler, means hot diffuse low density gas. And that's why from those low density gas, following a particular process called recombination, emission lines can be produced. Yeah, this is why we are getting emission lines. Yeah, so there are so many other processes which I have not mentioned. There many ways are there by which lines can be produced. Yeah, but the basic physics is that. Yeah, means transitions happening in the atoms. Now, whether the transition can take place or not, that will be dependent on different processes. So, in case of B-type emission line stars, we get emission lines mainly because of recombination process. Yeah, but if you only take the spectra of a star which is not surrounded by any gas or any dust cloud or something, then you will only see absorption spectra. That's all.
Sir, can I ask you a question, please?
Thank you, sir.
Yes, yes, definitely, sir.
Sir, first of all, I would like to thank Subhankar for bringing you on the board, and it was a wonderful learning. The moment you
Thank
started
you.
the presentation, I was thinking that when will you speak about Meghnath Shaha and the stellar
Definitely.
spectroscopy?
Yeah, yeah.
So, because that is really a fascinating thing. I really don't have any question, but I wanted to thank you because the way you have guided us right from the history of Isaac Newton to for lines and then into stellar spectroscopy, the classification of stellar spectroscopy. It's really wonderful. I would have requested you more to stay and spoken more about the classification, a little bit more on the stars,
Definitely, that
especially.
can be a different talk,
Yeah,
completely
absolutely.
different talk.
How
Because it's
the
very interesting.
JWST is, yeah,
Yes,
picking
yes.
up the photographs, etc. But I just want to thank Shubhankar and to you, sir, that it is really a wonderful and a very enriching and a very learning session. Thank you very much for teaching us everything.
Thank you. Thank you. Yes. Okay, so I guess there are already two questions in the box. So maybe I can answer that. Okay, Sharika, you have already asked a question. Won't interstellar gas and dust also contribute to the spectrum obtained from a star? Definitely, wonderful question. If so, how can we separate the spectrum of the star from the interstellar gas and dust? Wonderful question, Sharika. Yes, the place where we are situated is Earth, and if we take the spectra of a star, we know that in between the star and our Earth there is interstellar space, which has some gas, dust, and all these things are there. Maybe very tenuous, but it is there. When we take the spectra of a star, as I have told, the way I have told is a very 40 minutes of very simple understanding about spectra. But when we, after reducing the spectra, when we get the original spectra, if I can share the screen, I can show again. So then, apart from the lines or apart from elements contributing from the stellar photosphere or disk, we also see contributions coming from interstellar gas and dust. We also see contributions coming from forbidden lines. We also see contribution coming from our own atmosphere. Earth's atmosphere also has elements. They will also produce lines. So these all will be imprinted. But we have very proper understanding at what particular wavelength interstellar gas and dust of particular elements will produce some line. Also, we have very good understanding our atmospheric lines will be, these atmospheric spectral lines are known as telluric lines. Now these atmospheric telluric lines will be produced at what particular wavelength, we are very sure. These are very well studied things. So now if I show the spectra, if I open my PPT and show the spectra again, see this spectra. This one. Here you see I have already marked, right? This is H alpha, H beta, H gamma, H delta, Fe2. Now you see there is a line here, right? This is molecular water vapor coming from our atmosphere. Yeah. So now you see there is a line here. Here. This is at 6,284 angstrom, 6284. This is not due to any element from the star. This is an absorption line which is coming from interstellar gas. And any particular spectral line originating from interstellar dust and gas, we call it as diffuse interstellar bands. So it will produce a band like this. This is a very strong line coming from molecular water vapor from our atmosphere. So we know these things. We have very good understanding at what particular wavelength these lines will be produced. Again, you see there is a huge line here. This is due to molecular oxygen coming from our atmosphere only. So this is how yes, contributions from our atmospheric elements, from interstellar gas and dust, these are also there. And these are also superimposed on the spectrum after even normalization and reduction, but we know them. And the book which I will be sharing, that's why I told that I would like to share a book. The book which I will share in that group, you will see there are chapters, telluric lines, atmospheric lines. Even there is a chapter that if I switch on a neon light at night, that light will also give you that neon is also gas, that will also give you spectral lines, but we can separate it. At what wavelength neon light is producing, or sodium vapor lamps are producing spectrum, we can separate that. So we definitely take the spectra from telescopes which are situated at remote places of our country and world. We don't expect neon light vapor lamp will send some contribution. But if it is coming, we can separate it. Definitely. It's a wonderful question. Yes, yes. Okay, Kamal. Yeah. So there is a citizen science project on it. I guess, yes. I am not that much sure about scope. So maybe Shobhan sir, the people who are already in this group, they are much more experts in citizen science projects. So I guess, yes, there is a particular project on spectroscopy, which is scope. Yeah. Yes. And can we get PPT? Yes, we can get I can give the PPT in the group also. Yeah, no problem. I can share the PPT. Yes. And yes, can I receive more this class in future? Definitely you can. Yeah, so if suppose I'm giving any other talk, or as we are also planning that we can arrange some basic stellar spectroscopy or astronomical spectroscopy course for citizen science people or for students. So that will be also like a webinar series. So if we can organize that, definitely you can definitely join. Yes. So Kamal, yeah, is it possible to plot spectra in UV or IR range? Yes, definitely. Because you see, when I have told about Lyman series of lines of hydrogen, which is coming at 1000, 2000 angstrom. So that 1000 to 2000 angstrom means what? It is UV part of the spectrum. Then IR means, suppose if you go to higher Paschal series, then bracket series, then these lines will be formed at IR region, 10,000, above 10, beyond 10,000 angstrom. So in UV, optical and IR, we can plot the spectra as I have shown you. So ours was optical spectra, very easy to see. And UV and IR also, we can plot the spectra. But other places, other domains, we cannot plot the spectra. Yeah, because in higher energy domain, X-ray, gamma ray, means in those cases, we receive the signal in counts. Yeah, not in the form of continuous radiation. So we have gamma ray spectra also, but that is different from what we have shown. But in UV, IR, and optical, we can plot the spectra as we are showing digital spectra. Yes. Yes, we can get their spectra easily. Yes. So there are so many surveys, top surveys on IR, on optical, on UV. Yeah. So that we can get. Plants also, we can plot. Yes, definitely we can. So living beings, plants, we can in optical, IR, and UV. We can plot that if we take the spectra. Yes, yes. Yeah, Joseph, are you telling something? I'm not getting properly. Okay, so there is another question from Gourav Banerjee. Sir, considering Hubble's law, does the spectrum of our star shifts due to redshift? And if yes, doesn't it create any? Yes, thus your question is also very, very tricky and very nice question. Yes, I will tell you. So I can give an example. See, I have already told that uh, checking us real spectra of a star and doing some science is a very tricky thing, and very interesting also, because it is tricky, because nature has everything to confuse you, but nature is also very simple if you understand the basic physics strongly, and if you are interested to do, means, the same work hours after hours, days after days, years after years, without becoming bored. So then nature can reveal its secret. Now what I am trying to say is, yes, when you take the spectra of a star or any object which is moving towards us, it will show you blue shift. And if it is moving away from us, it will show you red shift. But I have also mentioned, to actually observe in a spectra, to actually basically low resolution spectra, or suppose you take high resolution spectra of a star, if the star is nearby to us, suppose a star which is 100 light years away, one even 1,000 light years away is also considered very nearby stars. So these stars will show you red shift or blue shift so less that it will become almost undetectable. In the case of spectra. So, and also we will understand that you can calculate. So from Hubble's law and from this redshift blue shift from Z law, means you can calculate how much redshift and blue shift will happen. And if you increase the distance, when you check the spectra of a galaxy, which is lakhs of light years away or crores of light years away, there you will get a definite, proper, identifiable lines which are blue shifted or red shifted, that you can understand. Yeah. And again, by physics, we can calculate that if this is the distance of this object, then how much should be the red or blue shift. So for this particular purpose, we need not have to worry. You see here, this particular star, which is around 1,000 light years away, you see the star has shown the H alpha line at very specifically very near to 6563 angstrom. Now there is obviously there is a shift. There are shifts which will happen due to instrument also, different instrumental parameters. But you cannot say that this shift has happened 5 angstrom or 4 angstrom because of blue shift or red shift. Yeah, you cannot say that. So because of blue shift, this star is showing a 4 angstrom shift. In that case, all the lines will be shifted 4 angstrom. Exactly 4 angstrom, which will not happen in this spectra. These are basically instrumental shifts. And second of all, these are nearby stars. So if you calculate a star which is 1000 parsec or 1000 light year away, at what speed it is moving towards us, suppose it is moving towards us as 20 kilometer per second, then what will be the shift? How much the shift it is expected? In these low resolution spectra, it will be undetectable. So you will get the lines almost in the similar places where it should be. But in galaxies, there will be shift. In quasars, there will be intense shift. And that can be studied and that can be calculated. Definitely. Yes. Okay, so yeah, Vignesh, will the gravitational waves also show Doppler effect? You see, gravitational waves is different thing. It is not, see, gravitational wave is a deformation of space-time itself, space itself. So that shift which, or the effect which it shows, it is known as gravitational redshift. It is not for Doppler shift, means an object moving away or going far near or far away from us. Gravitational wave is happening at the fabric of the cosmos. So that will give you something known as gravitational redshift. But if this gravitational redshift or effect is happening for an object which is very, very far away, that will also be very much critical to understand. Very, very critical to understand. Yeah. So For an object moving away from us or coming nearby to us, we can understand as it is an object. We can calculate that. For gravitational redshift or blue shift, we can detect up to a certain level of it, as this is happening in the fabric of the cosmos for a very far away galaxy or galaxy cluster, very bigger objects. So for a star showing gravitational redshift, it is almost nowadays also it is almost undetectable. And nearby objects, you will not be able to detect any gravitational shift. Means nearby, by mean of nearby, I also mean nearby galaxies also. See, in the cosmic frame, means 1 crore light year is nothing, basically. Yeah. So stars which are thousands of light years away, their gravitational redshift, we till now do not have that technology to detect their gravitational shifts. Yeah. So, but if we can detect in future, definitely we have to count it into account. That will be very, very small, which will not affect the physics of the star or physics of what we know. Yeah, this is the thing. Now, yes, Kamal, yeah, you are asking that can spectrum change depending on where we are looking at sun surface? No, it will not change, because the thing is that when we are looking at a star or a sun, we are looking at its surface, means we are looking at the photosphere and we are treating it as a point object. Because now comes the distance. Means for this particular question, means distance matters. So when we are taking the spectra of a star which is light years away, which is basically very far away, so the telescope is taking or the getting the radiation from the whole star surface. Yeah, so we are not getting, means part of the star surface is giving us information, another part we are blocking. That is not happening. It's a very far away object, is a point source. So we are getting the information from the whole stellar photosphere. So we will be able to tell in generally about the stellar photosphere, and there are other processes by which we can say that in that stellar photosphere what is happening in different parts of the stellar photosphere, like by studying the star spots, by studying astroseismology and all these things. Yeah, so like this we can do. Yeah, definitely. Yes. So yeah, so Mr. Dash, in solar spectra, is amount of yellow color more than the other color? Yes. So
Uh,
I feel.
Sir, I'm Rinku Das, not Mr.
Oh, acha, acha, acha. Oh,
I'm
okay,
Mrs.
okay, 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 okay.
Yes.
Yes,
Uh,
yes. In solar spectra, means solar spectra means, I will not say solar spectra. Actually, sunlight or sun produces maximum or emits maximum radiation at a particular temperature region, which gives it blue, yellow color. So this particular thing is governed by something known as Wien's law, which tells us that
okay.
at what particular wavelength or at what particular temperature a particular body will emit the maximum amount of radiation that can be identified. Yeah, so for, I will not say solar spectra. So when you take a particular body having a particular temperature, then you can calculate what color it will be, by using.
Actually,
Yeah.
sir, my students have asked one questions that in some in noon time, we generally see the grasses, the green grasses, looks like some yellowish. So why does it looks
This is due to
yellowish?
diffraction, all these things, diffraction, reflection, all these properties. Yeah, this is nothing to do with the, means,
Uh,
because the actual color is
connection
not
this.
changing. Yeah, yeah, yeah. Yeah, so this has nothing to do with spectroscopy or the color is changing. Actually, no. No, or we see sunlight, means reddish color during the time of morning or evening. That is not that the sun is emitting some other radiation. No, it's because
No,
of
no, no.
reflection effect and all these things. Yeah.
Yes, but you just say na that the yellowish color is more dominant in the solar spectrum.
Solar spectrum, yes, yes. Yeah, but there are other things which will dominate in case of, morning and evening sessions. If there is reflection, scattering, light scattering, so many other physical processes
Yes,
start dominating. So that will
that
change
is
the color,
also
but not the sun's color. Yeah, so if suppose anybody else from any other planet is also taking solar spectrum at that moment of time, they will also see yellow color. Means sun will be yellow color. Yeah. Or any other person or any other life from outside our earth is taking the spectrum or looking at our sun, they will also see yellow color. So from our earth we are watching during morning time some other color is because of different process. It has
Yes,
nothing to
that
do
is
with
true.
sun. Yeah, it is nothing to
Yes.
do with sun. The scattering of light, scattering processes and reflection on all these things. Our clouds also help in this scattering. So this is why
Hmm.
we see an apparent change. It's not because see, sun is actually not red. Yeah. Or our sky is actually not blue. That
Hmm.
is happening due to particular hygroscopic nuclei effect of water vapor and water molecules, especially air molecules. So this is, but the reality is the sun emits the most amount of radiation at a particular wavelength, and which turns it, which gives it yellow color. So anybody from any place of our universe, if they can photograph sun, they will see a yellow star. Definitely, yes,
Yes,
yeah.
and also
So
the violet color is less present in solar spectrum, na?
yeah. Solar spectrum actually see violet mixes with bluish color mainly. So we will not see suddenly a violet star. Yeah. Means violet is very much near towards bluish, the dominant towards bluish. So we see blue, but violet thing we will not see. Yeah, this is our eyes are not sensitive that much to violet. Yeah, this is the thing. Uh, yes, yes.
Okay, sir. Thank you.
Yeah. So okay, yeah. So thank you, Joseph G. Yeah. Thank you everybody. Thank you the organizers. So yes. So yeah. There is one more question from Gourav Banerjee. One more. Can we observe spectrum of a yes? Definitely. I will give that book, right? You will see the supernova spectrum. Yes, nova spectrum, supernova spectrum. Yeah. And it will form a neutron star or a black hole. That we can, because yes, we can. Means from spectrum also we can. We can understand by looking at the supernova, understand by study. The people who are studying supernova, they can predict the mass of the star or the progenitor star which burst it. And from that they can predict whether it will become a neutron star or a black hole. Yes. But yes, it is difficult to observe. Yeah, but supernova spectrum, yes, it is available. Yeah, definitely you can see supernova spectrum. Yeah. Okay, book name. Okay, so okay, let me share the screen and I will show the book. So anybody can also download the book. This is available somewhere. Definitely, it is available in Library Genesis and other places. So anybody can download the book. This is Spectral Atlas for amateur astronomers. This is the, I guess here the internet is slow from my end. So I'm putting the book name. Yeah. Oh, thank you. I'm very happy. Yeah. Yeah. So I'm putting the book name. Let me share the screen. I will show the book again. So it again got cut to internet issue. So this is the book. Spectral Richard Walker Spectral Atlas for Amateur Astronomers. Yeah, this is the book. You can download it from Library Genesis and other places. And I will also put the book. So it will page by page, it will show how the spectra of a star, nova, different type of star, how atmospheric spectra looks like, everything they will show. And here also I have put the name of the book in the message box also. Yeah. So this is the book. Okay. I hope now again I am audible. You can contact me by WhatsApp. I am giving the WhatsApp number. Yes, this is my WhatsApp number. Anybody can contact me if you want. Yes.